Hi, my name's Fred Zott. I'm a geologist living in Pittsburgh, and I'd like to share with you an invited talk that was delivered to the annual meeting of the Rachel Carson Trails Conservancy yesterday evening, May 1st, 2024. So let me get the slideshow started here. Going to share the screen, and here we go. It's the geology of the Rachel Carson Trail, the land between the rivers. First, we'll talk about the regional geologic setting and some key concepts that will help in interpreting the features that you see along the trail. There were rock kits on the table with the participants last night. We learned to identify sandstone, siltstone, mudstone or shale made of clay, limestone that can be marine with marine fossils, and coal. We learned to identify the rock types that you find along the trail here. We're in the low plateau. The oval shows the area of the trail sandwiched between the Allegheny and Ohio rivers, where the rock layers here, the sedimentary rock layers, are pretty flat lying, some broad folds, but pretty flat lying, low relief folds. In contrast to the east, in the high plateau of the lower highlands, there are big folds, even more intense folding in the Appalachians, the Valley and Ridge. Those folds were created by a mountain building episode about 300 million years ago, with mountains that were as high as the Himalayas once, say in the area around Philadelphia, created by collision between the African and North American continental plates. But here we're in the low plateau, and you'll see what the rock layers look like in the best outcrop of these strata in the region along the Ohio River next to the town of Brilliant, Ohio. Here's the Brilliant outcrop. It's over 300 feet tall, 8/10 of a mile wide. You see these flat-lying rock layers. In the center is the Morgantown Sandstone, that band. We'll take a closer look at the middle of this outcrop. There you see the cliff-forming Morgantown Sandstone has an erosional base, river channel deposits within it above the dashed red line, the river channel cutting out shales laterally. Below that, the white band is the Ames limestone, a relatively thin unit that was from seaway flooding into this area, depositing this limestone with marine fossils. Below that, you see another dashed red line with floodplain shales cut out by another river channel with river channel deposits within it. And there's another key marker near the top of the outcrop. That black band is the Pittsburgh coal. So lots of variability in rock types vertically, but also laterally because of the river channels and lateral changes. These are as a map of the kinds of depositional environments 300 million years ago in the area. There would be river channels with sands within the channels, carrying sand from the mountains off to the east and south and southeast. In between rivers were floodplains with clays, silts, and sands deposited. There could be lakes there with lacustrine limestones. There can be peat swamps that formed coals when they were deeply buried. The mouths of the rivers can have sandy deltas and shoreline deposits. Offshore shales and clays were deposited. At times, the seaway flooded across western Pennsylvania, and marine limestones like the Ames were deposited over a broad area. So those are the types of depositional environments reflected by the rocks. Here's a schematic vertical section of the rocks. You can see the scale in the lower left. The double-headed arrow indicates the rocks that are exposed around the trail area, and the rock types are shown too, with yellows being sandstones. Shales are shown as brown or gray or red. Marine limestones are medium blue, non-marine limestones, lacustrine limestones are in light blue, and coals are in black. And key layers we'll talk about from top to bottom: Pittsburgh coal, the Morgantown sandstone, Ames limestone, and the Upper Freeport coal. You can see in this schematic that in some places there are lots of sand deposits, sandy river channels, and other places it's a shaly or vertical section. This is a geologic map of the area. The trail is shown in yellow. The areas that will focus and see some highlights of geology are shown with the red bubbles. And on the side is the vertical section of rocks that I mentioned before. Every time we see a geologic map, we'll see that, and we'll see a box around the rocks that are exposed in the trail area. A couple of the key markers here, though, the boundary between the yellow and brown rock units is the Pittsburgh coal. So the Pittsburgh coal is exposed on the side of Mount Washington here at the bottom of the map, formerly called Coal Hill. The Pittsburgh coal is only preserved in a few of the very highest hills just in very small spots in the area of the trail. The rocks at the surface are generally older than that. But the upper Freeport Coal is the boundary between the yellow and green rock layers. And you can see from the geologic map that that boundary is at the surface in part of the trail area. So we will look at the Freeport Coal in the Bailey Run area. You can see the bubble again of the area of the trail, and the white lines now indicate as far south as glaciers ever came in the 2.6 million years since there have been Pleistocene glaciations. So the area wasn't directly affected or overrun by glaciers, but the terrain here certainly was affected by glacial times. And we'll talk a lot about that. The river systems were the way that the terrain was affected by glaciers. And before glacier times, the Allegheny River is thought to have been in three pieces. The river systems here all flowed to the north, drained to the north, including the Upper Ohio River draining from Pittsburgh to the north. But when glaciers came, the rivers couldn't flow north anymore. The Allegheny River was forced to amalgamate in front of the glaciers, and the whole river system now drains to the south into the Ohio Valley area of Kentucky and southern Ohio. Well, before glacier times, the river valley in Kentucky and southern Ohio was at a lower elevation than the rivers here in western Pennsylvania. So when the rivers were forced to amalgamate, one or more waves of erosion worked their way up into the river system, deepening the river valleys here by quite a bit. And that includes the tributaries of the Allegheny River in the area of the trail. To identify evidence of that deepening, it's helpful to have the concept of an ideal stream profile, with this being the elevation of the base of a stream or river from an upland area where it's relatively steep on the right, coming down to a lowland area and low gradient stream or river, coming into a base level, which could be the sea or a lake, or maybe a larger river on the left. If the base level drops, as happened when the river systems in western Pennsylvania amalgamated with the rivers at a lower level in Kentucky and southern Ohio, then a wave of erosion works its way upstream as the river tries to reestablish a new equilibrium profile. And the frontier of erosion on the stream or river is manifested by that convex upward shape in the elevation profile. That's the head of erosion working its way upstream in a stream profile that's otherwise concave up. Notice the dashed line, that's the previous level of the stream that's now incised. If the stream was at that level, or river was at that level for a long time, it may have developed a broad valley. And when the erosion works its way upstream, it could incise into that valley and leave behind flat terraces that reflect the ancient level of the river valley there. If you have more than one drop in base level, more than one wave of erosion working its way upstream, then you can have more than one of those convex upward erosional zones working its way upstream simultaneously, and you can have more than one terrace perched high and dry left behind as the stream incised down. Here's a real stream profile. This is from Mingo Creek in Washington County that drains into the Monongahela River. And this good example comes from a master's thesis at WVU. Look at the upland area on this profile. See how smooth the elevation profile is? They're probably reflecting a pre-Pleistocene, pre-glacial, smooth elevation profile. There are prominent terraces along the sides of the Monongahela River here, where the river used to be before glacial times, and it cut down about 200 feet. So those terraces may reflect the equilibrium profile that connects with that upstream area. Well, Mingo Creek was forced to cut down as the Monongahela River cut down. So here's the current elevation profile. It's steeper here where there's erosion, and the frontier of that erosion is called a nick point, and the zone of erosion is called a nick zone. Those are terms that we'll use a bit later. Notice the convex upward shape at the nick point. Here's a really good example of terraces from Lower Chartiers Creek. You can see the Ohio River in this elevation map in the upper right. Chartiers Creek flows into the Ohio at McKees Rocks. And along the flank of the Chartiers Creek Valley in Crafton-Ingram are these beautiful terraces. You can see red and white of the typical hills outside of those terraces. And look at this yellow elevation terrace. It's pretty flat, has these smooth edges. I hope you can imagine ancestral Chartiers Creek having carved those edges and deposited a terrace there, formed a terrace. Then in the lower Ingram area, clearly the Chartiers Creek cut down, formed another terrace with green elevations before it incised a little farther to the current elevations lower down. So those are the two representative elevations from those two terraces in Crafton-Ingram. When we look at an elevation profile, again from that WVU master's thesis, you can see that way upstream on Chartiers Creek, past Washington, there's a smooth elevation profile, probably the pre-Pleistocene profile, that may relate to that upper terrace in Crafton-Ingram. Currently, the Ohio River is at a much lower elevation. It's cut down by a couple 100 feet or so. And Chartiers Creek has been adapting to that. The frontier of erosion, the nick point, you can see in this elevation profile. And this green elevation was a terrace kind of along the way as the stream cut down. So good example of stream terraces. And the process by which this downcutting happened could have been a complex process. This is a map of global climate for the last 5 million years or so. Warm is toward the top, cold is down toward the bottom. And Pleistocene glaciation started about 2.6 million years ago. You can see lots of climate alternations since then. Present day is on the right. The timing of when glaciers made it far enough south in Canada to block the north-flowing western Pennsylvania rivers, that timing is not well known, but there is recent evidence that suggests it could have been as long ago as 1.8 million years. There have been lots of glacial, interglacial climate cycles since then. So in detail, that process of erosion and deepening of the valleys and tributaries could have been a complex process with more than one wave of erosion. Another feature that's helpful to understand the rocks along the trail are natural fractures. Picture this as a hard sandstone layer. It's cemented more than a mile deep in the subsurface. And that tectonic event happens, the mountain building episode that produces some broad folds in the plateau area. A couple of different fracture sets can form. In blue are fractures more or less perpendicular to each other, the orthogonal fracture set. And in red are shown fractures that are an acute angle to each other, oblique fractures or fractures I call conjugate fracture set. They may both be present in a rock layer, or there may be only one of those in a given rock layer. But you'll see those along the trail. The last feature I'd like to describe to help you understand the features along the trail in the rocks is cross-lamination or cross-bedding. This is a flume. It's like an aquarium. It's got a glass side. There's a flow of water, and there's a sand dune marching across the bottom of the flow of water. You can picture sand grains bouncing along the top from left to right. And then when they come to the inclined surface in the front of the dune, there's an eddy in the water current, and the sand grains drop out. And the sand dune marches from left to right, marches downstream, and leaves behind those inclined traces that show by the inclination which way the flow of water was from left to right. So we'll see those traces in rocks along the trail too. So that's it for the general geology. Now we're going to move into more specifics in the land between the rivers, Rachel Carson Trail. Here you see the trail on an elevation or a relief map. The trail crosses Bull Creek, Deer Creek, and runs along and across Pine Creek for some distance. Pine Creek will be a focus for us. But this is why it's such a challenging trail, because it crosses those drainages, and those drainages were deepened in glacial times by the deepening of all the river systems and their tributaries. This elevation map helps to highlight that. You can see the river system, it's say 400 feet deep at Pittsburgh, the Ohio River, the Allegheny, and Monongahela. You can picture Mount Washington 400 feet high. Well, it was only 200 feet deep before this glacial caused erosion worked its way up the rivers. And that erosion has worked its way up the tributaries too, like we saw with Mingo and Chartiers Creek. So that's part of the reason that the trail is so challenging. There are 5 focus areas where we'll look at some neat geologic features along the trail, and a couple of those are right along the edge of the Allegheny River. Another feature along the rivers are these flat terraces. So this is Natrona Heights. See how smooth and flat that is compared with the upland area next to it? Well, that's an ancient river terrace. The ancestral Allegheny River ran along there, deposited sand and rounded pebbles and cobbles. Sand and gravel were mined along the edge of it. It's a very well-known Pleistocene river terrace. And now that your eye is cued into that, I hope you can see others along the edge of the river too. Here's one, the upper part of Springdale. There are others. And when you compare those with where people live in concentrations, people tend to live, a lot of people live on those terraces. They were good places for building communities because it was flat ground and they were well above the current river level. They weren't susceptible to flooding. So if you flip back and forth between the two of those, you can see that a lot of people live on those river terraces. Okay, let's start with Harrison Hills Park and we'll work our way west with those focus areas. There's the trail going into Harrison Hills Park. You can see the trail, part of it is perched on the bluff above the Allegheny River. This is a geologic map. You can see the part of the section that we're in, Ames limestone, is in some of the highest points in this terrain. But on top of the bedrock are terrace deposits. So these terrace deposits of Pleistocene age, they never were deeply buried. They weren't buried more than a mile deep like the bedrock and cemented into rock. It's loose sediment. And we're going to look at two of those, the northern two of those terrace deposits we'll look at, including the one that's right along the trail. These are elevation profiles of streams in that area too. Rachel Carson Run crosses the trail at Rainbow Bridge. And you can see from the elevation profile of Rachel Carson Run, this clear convex upward shape at Rainbow Bridge. That's an area of active erosion, bedrock in the stream bed there. And we'll take a close look at that. Look at the other elevation profiles too. Those show convex upward shapes too, where there is a frontier of erosion working its way up into this flatter kind of pre-Pleistocene landscape. We're going to zoom in on the area of the red box. Here it is. You can see a more detailed map of the terrain. You see the yellow trail there too. The overlooks, that's the northern of those two mapped Pleistocene terraces where the ancient river used to run. It's 250 feet above current river level that are these flat terraces. Working our way south, here's Rachel Carson Run. There's bedrock in the stream around Rainbow Bridge. So there's ongoing erosion there. You can see the nice cascade with Rainbow Bridge where the Rachel Carson Trail crosses Rachel Carson Run. The landscape below the bridge has this young V-shaped, strongly erosional valley. And then you go above the bridge, you lose bedrock in the stream bed, and it's a broad valley, that pre-Pleistocene landscape. There are natural fractures exposed in the stream bed where the bedrock is exposed near the bridge. I hope you can see this straight line and fairly planar surface. That's a natural fracture. There's another one here, an orthogonal fracture there. These are subparallel to the orientation of the stream. These streams in the strongly erosional landscape tend to take advantage of zones of weakness as they cut down, and often the streams will parallel major natural fracture sets. Here you can see the fracture orientations I measured here in Rachel Carson Run, plotted up, and clearly you can see the blue orthogonal fracture set pretty well, and there are some conjugate fractures shown in red as well. Moving farther south along the Scouts Trail, the soccer fields were built on the southern of those two highlighted Pleistocene terraces, a nice flat terrace to build a soccer field. But you go east of the soccer fields where earth has been moved, and east of there are older trees growing, and I don't think the earth has been moved. I think it's in place. It's a good place to look at the terrace deposit. See this nice bench, good place to enjoy the view next to Scouts Trail, and just downstream of it, there's 300-million-year-old sandstone bedrock in place. So there's a veneer of sediment on top of that from the ancestral Allegheny River. We're going to look next to one of these trees that's behind the bench on this terrace. And here you see around the roots of the tree, sediment that's been in place since before the tree was growing, so it's not been moved by people. Nice rounded pebbles that once rolled on the bottom of the ancestral Allegheny River, 300 feet above the current river level. So a good example of a Pleistocene terrace. Now let's move to the Bailey Run area. Here's the trail in Bailey Run, and the part of the trail we'll focus on is just south of Bailey Run and Bailey Run Road in this area. Here's a geologic map. The blue line is the Ames limestone. The trail does cross it. I don't think there are good outcrops of it here, though. It's a pretty smooth terrain up there. But look down in the valley. See the colored change between medium gray and lighter gray. That's the level of the upper Freeport coal, which in places in this general area was mined at the surface and also mined underground where it was thick enough. And the trail crosses that upper Freeport coal. So we'll take a look at that too. Here's a more detailed terrain map, and we're going to take a close look at quarries. One that's down deep in the valley next to the road. We'll take a good look at that one. And then we'll look at a couple of levels of quarry, a lower one and an upper one that are right along the trail in the lower of the southern of the two blue ovals. We're going to look at the coal first, and those black circles indicate the places where we'll look. First, upstream from the trail along Bailey's Run Road is a road cut of Freeport coal. It's about 7 or so feet thick. It's pretty thick. Freeport coal's not that thick everywhere. It's kind of patchy in its thickness and distribution. This is the lower quarry that I pointed out in the terrain map, the one that's near the road. And you can see the coal's exposed in the upper part of the quarry here. Here's a chunk of coal that fell down, and you can see a rock hammer for scale next to it. But this quarry clearly wasn't dug just for the coal. The quarry mined into rock way below the level of the coal. So it was mined for rock other than just the coal here. Now, across the river, or across the stream and across the road, opposite this exposure of coal, we'll see another place where there's coal at the surface. Here's the Rachel Carson Trail starting to climb up the hill, cross the valley from that quarry, and you can see a switchback here. And in the switchback, there are bits of coal in the trail, upper Freeport coal. There's some coal laying on the ground nearby. There's a place where people dug into the hillside at the level of the coal nearby too, but there hasn't been much surface mining of it here. It was mined at the surface and in the subsurface in the general area, but not right here. So down deep in the valley, that's where that upper Freeport coal is. Trail crosses it. If you go farther up the hill, here's the lower of those quarries. It's all overgrown, this old quarry. There are no bits of coal here. It's not a quarry for coal. It's a quarry for another earth resource. And I think we get a hint of what that is in the upper quarry, which seems to be more recent. The top of the skyline here is held up by sandstone, and below that there's lots of shale exposed at the surface, bits of shale that have come downhill from the quarry. So I think this was a shale quarry. I think it was a clay quarry, and we know there was lots of brick making in this area. I don't think these were coal mines. Other rock types that you find here, there's some nice flecks of mica in sandstone. You can see them winking in the sunlight. Here's a bit of sandstone, a natural fracture surface, has manganese oxide, which can have a crystal habit that's shaped like ferns, as you can see here. Some other neat rocks that you see traces of life in the thin sandstones. There are traces where living things burrowed through the sand or crawled across the top of the sand. I think those are marine trace fossils. It wouldn't be a big surprise if there were marine deposits here. This is the part of the section that has those marine limestones in it, the Glenshaw Formation. So it wouldn't be a big surprise if there were some marine deposits in the area of this quarry too. Up at the top of the quarry, this is the sandstone. I hope you can see the cross lamination here, the laminae coming down from right to left, indicating the ancient current in this layer flowed from right to left. There were 5 beds I saw there with cross bedding. I measured them. You can see them reflected in the rose diagram. They're flowing kind of to the south, and they have a couple of different orientations. That could be consistent with shifting tidal currents. It doesn't really fit the more or less northerly direction of river deposits in the area that we'll see later. So could be a tidally influenced little sandstone deposit. Wouldn't be a big surprise. Now let's move down to Springdale. There's the Rachel Carson homestead right along the trail, and it's in a really pretty neat spot in terms of the shape of the land. There's a long slope. The homestead is just at the top of that long slope, and on top of above the homestead is a flatter area that's a Pleistocene river terrace. You can see that it's sediment's been moved around. This is an athletic field. It takes advantage of that flat terrain, but the terrain is in place here. The terrace, though, ends before the homestead. The homestead is on this long slope. This is not the way I'm used to seeing edges of terraces. Usually, where I've seen them, they're sharp edges like these two, not a really broad slope. But this type of feature occurs in 4 or 5 other places along the river system. And I'd like to show you another one of those and then come back to here. I want to show you what this looks like near the trail in Natrona Heights. So here's Natrona Heights. It's that flat river terrace I showed on a previous map. Well-known gravel and sand was quarried from the ancient river deposits. But look at this edge here where it turns into a slope, like the slope in Springdale. You can see that edge. That's the Brackenridge area with Natrona Heights being on the terrace. The check marks indicate places where I went in the field and looked for in-place deposits that I could be convinced had rounded pebbles and cobbles and sand from that ancient river deposit. I looked around the area around the Bull Creek Trail parking area. The trail climbs up here, and it's actually on the terrace here, on the edge of the terrace. There are rounded pebbles there, but the earth has been moved so much by construction. There's a drainage ditch right next to the trail. I couldn't be convinced that there actually were terrace deposits in place. So I won't show you pictures of that. But I did go across the road, across Bull Creek, and scouted around this area too. And I found a really pretty neat fossil there. Really the neatest fossil I think I've found in years. It was right in the trail and right next to Route 28. So here's the trail climbing up to Bull Creek Road, right next to Route 28. There's been a lot of movement of the earth here as Route 28 was built. There's a boulder of kind of sandy limestone sitting in the middle of the trail here. And look at this coiled fossil that's on that boulder, right in the middle of the trail. Here's a closer view with my Schufer scale. I think that's a coiled gastropod or snail shell, I think from a piece of Brush Creek marine zone. There are other marine fossils in that too, not just this large one. So pretty neat fossil and right in the middle of the trail. As far as I know, it's still there. Okay, back to the Carson homestead. You remember the picture here with the terrace. There's a map, Pleistocene terrace, in this 100-year-old map around the Carson homestead. I'm going to show you terrace deposits here on the top of the bluff, and they seem to have missed those 100 years ago. Nobody's perfect, I guess. So that's the first place we're going to look. And around the roots of these trees, sediment that's been in place for a long time. People haven't moved the sediment there. It's in place. You find lots of rounded pebbles that once were rolled along the bottom of the ancestral Allegheny River. They include rocks like this. This is granite. That's an igneous rock. There's no granite in outcrop at the surface in northwestern Pennsylvania. This was plucked up by glaciers in Canada, no closer than the middle of Ontario and maybe farther away than that. That's the closest outcrop of this rock type. The glaciers would have picked up, plucked out of the outcrop, dragged to the south, and then washed into the Allegheny River system, and it rolled along the bottom of the river and got rounded like this. And there are other rocks, crystalline rocks like that here too, that are clearly traveled from Canada in a pretty complex path. Now let's look at what I call a power view, a pretty neat viewpoint. You can see on the satellite image, it's along power lines that give a viewpoint of the Springdale Power Station. Pretty neat view from the trail there. Springdale Cemetery is a little bit off trail. I looked at that because it's flat. I think it's part of the Pleistocene Terrace. And it's pretty neat that there's a branch of the Mullen family in this nice old cemetery. Carson Homestead itself, right on the trail, place where Rachel Carson grew up, nicely preserved. You can see it from the front. I took a look around the back. You see the slope here that I talked about before on the maps. And There's some rounded pebbles mixed in with the soil, but there also here is a piece of terracotta pipe. There's coal, there's glass, things that obviously people brought to there. So I can't show you sediment that I'm confident is in place in a terrace deposit. It looks more like slope wash to me. On the west side of Springdale, you can see this really flat terrace with benches below it. This is a slag deposit, a slag heap. And we're going to look where the red circle is. And beyond the well there, that flat top of that terrace is the heap of slag, the slag dump west of Springdale. Okay, we'll move to cold valleys now, a little farther west, and we're going to look at both Crouse Run and Rocky Dell. Both of them are shown on this map of the trail. We're going to look at both of them. They're both steep-sided valleys. They're known for their flora that's more typical of Canada than here, kind of microclimates in these protected valleys that are shady much of the day. On the satellite image, you can see that they're nice natural areas, the trail traverses in both Crouse Run and Rocky Dell. There's the geologic map. Crouse Run and Rocky Dell, the rocks there are below the blue line that is the Ames limestone. But first, we'll look at a level that's above the Ames limestone. It's the level of the Morgantown Sandstone, and there's actually a sand pit where Morgantown Sandstone was mined. You can see the excavation of the sand pit on this detailed terrain map from a LiDAR image. Look how smooth the hilltops are around the sand pit. The sand there that's up near the surface now was clearly near the surface for a long time. It's been exposed to groundwater, rainwater percolating into the ground for a long time. Very smooth profile of the tops of the hills. And when you look at the sand pit, it's almost like you've gone to Utah. It's orange rock, unusual for this area. Morgantown Sandstone has a different composition than sandstones above and below, and probably a different origin. It's not clear whether there was some tectonic event in the mountain belt or some change in climate, but it's different than the other sandstones. In a lot of places, it's cemented with calcite, and calcite will dissolve in groundwater, it'll dissolve in rainwater, and then you're left with loose sand. And that's what's happened in the sand pit. The groundwater has migrated through this sand. You can see bands of iron oxide, picture groundwater migrating through it. There are speckles here where there are some sorts of grains with reaction rims around them from the groundwater migrating through, but you're left with loose sand in the sand pit. Morgantown sandstone is widespread throughout the region, and in the early 1800s, it was used for construction, but they realized that when it was exposed to rainwater, the cement binding the sand grains together dissolved, and you don't want a building stone that turns to loose sand. So they learned in the late 1800s not to use the Morgantown sandstone for construction. But you do see old buildings in the region that are made of Morgantown sandstone. So pretty neat exposure, a little bit off the trail. Now we're going to move to Crouse Run. We'll look at some outcrops along the trail and also one that's near a memorial bench just upstream of the trail. That's the first place we'll start. You can see bedrock right next to the stream and also in the stream bed. I hope you can see the long natural fracture here. The stream is subparallel to that orientation of fractures. Look at these fractures. They're actually underwater, but you can see them. And those are orthogonal fractures. You can tell that this one was first because this one abuts it. A new fracture can't jump across an open existing fracture. So orthogonal fractures there in the stream bed. Farther downstream along the trail, you can see outcrops like this. These are two different outcrops. Look at this really soft shale layer, really soft clay layer. It sits underneath an inch-thick coal. That coal would have been deposited in a peat swamp. Peat swamp waters would have been very acidic, so the soil below the peat would have had a lot of material leached out of it and be a very special material today. It's the softest type of rock that we have in outcrop. And wherever you see that type of rock, ancient soil horizon, especially underneath coals, it'll always form an underhang. It's the softest type of rock that we have. Above that, there are some siltstones and sandstones. The slabby sandstone here, the thin layers, you can see that there are some nice plant fossils in that outcrop. Okay, let's move to Rocky Dell, and we're going to look at part of Rocky Dell where there is a steep-sided valley, and here goes the trail. There's a blaze. There's an outcrop right next to the stream. There's bedrock exposed in the stream too, and you can see cross-lamination here from when the sand was deposited about 300 million years ago on the bottom of an ancient river. There's another outcrop with cross-lamination a little farther downstream. I hope you can see the cross-lamination in these close-ups. The white arrows indicate the flow direction that the cross-lamination indicates. I measured those orientations, and they're plotted here. It's an east-northeast median orientation of the cross-bedding, 10 cross-bed sets. And I think that can fit with rivers and deltas in this area. It's thought that rivers came into this area from the south. You can picture the rivers kind of splaying out as they are in a distributary toward a deltaic area. So having an orientation like that, this could still fit with rivers in the area. There are natural fractures in the bedrock too. I hope you can see this one in the stream bed. This is visible from the trail. You just look over from the trail and you see this zigzag arrangement of natural fractures. I measured a bunch of natural fractures in both Crouse Run and Rocky Dell. You can see the results of those. There are, I think, orthogonal fractures well developed in both places, but at Rocky Dell, you start seeing this north-northeast, south-southwest orientation of fractures. And I was pleased to see that because look at all the stream valleys with that orientation, probably following a natural fracture set that's in that north-northeast, south-southwest orientation. So it was neat to see transitioning into that orientation of natural fractures that are reflected by the streams and the terrain at the surface of the land. The erosional valley here, it has steep sides, but here near the mouth, it has a flat bottom, and there's no bedrock at the bottom. There's sand, there are pebbles, there are slabs of rock, but not bedrock at the bottom. It's not actively eroding bedrock today, but the stream valley is widening and it has these steep sides. You follow the valley up and it turns into a V-shaped valley without that flat bottom. So it's a very young V-shaped erosional valley here. And this triangle indicates as far upstream as I found bedrock currently being exposed and eroded in the stream. So the Nick zone, or the zone of erosion, this is the way it's manifested in this terrain map. And I described that there's bedrock exposed in it too. And that's the frontier of erosion. Upstream of that, it's a much broader valley without that active erosion. And the Nick zone is right around where the stream crosses Hemlock Drive. Here's an elevation profile of the whole stream, not just the part through the Nick zone. You can see the mouth of it at Pine Creek down here. There's the convex upward zone of erosion with bedrock in the stream bed. The frontier of that erosion is here. And so you can see an elevation profile. And this is what it looks like on the ground. The steep-sided valley where it's in the Nick zone of active erosion. And then upstream of the triangle here, upstream of the erosion, a very broad valley. And there's no bedrock in the stream bed here. It's sand and gravel, not active erosion of the bedrock today. So now that we've seen a bit about elevation profile of a tributary to Pine Creek, let's look at the whole system. Let's look at an elevation profile for all of Pine Creek from the Allegheny River to the headwaters, as far north as you can go. So here's that elevation profile. The river's on the left, the headwaters of Pine Creek on the right. You can see distance in miles at the bottom. You can see landmarks that the stream crosses, including tributaries at Fall Run, Crouse Run, and Rocky Dell. There's North Park Lake. And this smooth profile, concave up as we expect in this upland area. There are some bumps along it, but I didn't spend a week measuring with a GPS device like was done for the master's thesis at WVU. This is done in a couple of hours from maps. So I'm not 100% confident that those are zones of erosion and convex upward zones in the elevation profile. You'd really need to verify that. But let's take a look at the tributaries and their elevation profiles, because you can clearly see zones of erosion on those, just like we saw along Rocky Dell. So there's the one along Rocky Dell around Hemlock Drive. We've put a check mark there because we've verified that as a nick zone, a zone of erosion with bedrock exposed. There's another zone like that close to the turnpike crossing on Crouse Run, but the part of Crouse Run I looked at in the field was downstream of Wildwood Road, where the Rachel Carson Trail crosses the stream. I didn't look that far up, so I haven't verified that one. It's got a question mark. Fall Run, if you've been there, you know the waterfall, so clearly that's a zone of erosion working its way upstream. Here's how it shows in this highly squeezed elevation profile that's made at the same scale as the Pine Creek one. If we stretched this out laterally, it would look more normal as a convex upward shape. There's another convex upward shape farther upstream, and you can see it on the map too, the terrain map. I haven't been up there to look at that one, so that one's got a question mark too. So clearly, you can see the zones of erosion working their way up the tributaries of Pine Creek. These are the levels of terraces above the river system. The terrace at Trona Heights was 250 or so feet above the river. Bloomfield, there are other terraces in between. Troy Hill is one. The upper terrace at Crafton, about 190 or 200 feet above river level. The lower Ingram Terrace we saw in lower Chartiers Creek, it's 90 or 100 feet above river level there. So this would have been probably the level of the elevation of Pine Creek before this Pleistocene age incision. Clearly, Pine Creek has eroded down quite a bit in the last couple million years or so. Okay, the last part of the trail we'll look at are western uplands on the western part of North Park. And we'll look at the area with the red circles there. In the geologic map, you can see it's above the level, and the red shows the Ames limestone. We're above that in the Castleman Formation. And on a topo map, you can see it's a pretty broad landscape there, pretty smooth landscape. You can see the smooth landscape in the LiDAR image of terrain also. And on the satellite image, the western of the bubbles is in a field. The eastern one is in a valley. We'll look at pictures of both of those. And here you see this upland area with really broad valley, flat upland field. There is a gully cut into the valley. It's not very deep, a lot different than the erosional features we saw at Crouse Run and Rocky Dell. And this one, as far as I know, hasn't been studied in detail, but I have read studies of features like this elsewhere in the region, a relatively small feature where they've done radiocarbon dating and they can age date when the incision happened. And these features can be associated with deforestation, when all the trees were cut down and the hydrology of the stream changed a lot and it incised a bit. So this is not necessarily a feature of Pleistocene erosion working its way upstream. It could have a very different and much younger, more recent origin. So those are the features that I'd planned to show you along the Rachel Carson Trail. I thank the Conservancy for maintaining this trail, and I really appreciate the chance to learn from it and to interact with the Conservancy members. Thank you. Have a good day.